Okay, um, let's look at some of the limit laws. And first, I guess let's start with a constant. Y equals C. C is a constant. This is the horizontal line. So, just if you sketch this, let's say C is here. Then if you pick any point on the x-axis, let's say A here, and let x approach it, then the limit is still going to be C. It's not going anywhere. So as you come in and approach A, your y, as x approaches A, then your y values just still approach C, the y-axis, that point C. So limit of a constant is a constant. What if you have any line, y equal mx plus b? Let me try that. So let's say here's our line. This point is B. The y-intercept's B. And let's try any point A. So here's A. And if x is approaching A from both sides, remember you have to think about both sides, then on this line, you're approaching this point. So the point is the line evaluated at A. So the name of that point right there is A, MA plus B. What we did was substitute A into the line equation. So the limit of mx plus b of any line is MA plus b. And we just did direct substitution. Substituted in A for x. Let's look at degree 2. Let's move up a little bit. That's called a quadratic. And we know those are parabolas. Let's just draw a parabola. And let's pick this to be A. And we'll take the limit as x approaches A of that parabola. And just looking at the picture, we see as x approaches A, our graph is approaching the y value that goes with A, so that's the point A. We substitute in A for x. I should have used a different A here. Let's call that, it's easier just to change one. Let's call that K. Okay, so that's going to be A, K. Substitute K in for x, and we get this point. So that'll be f of k, which is ak squared plus bx. So it's bk plus c, bk. And that's also direct substitution. And this is going to be true for all polynomials. Since they're nice and smooth, there's nothing funny going on here. So for all polynomials, you just do direct substitution when you do limits. You substitute whatever it's approaching in for the x, because that point does exist. Now if that point is not on the curve, then you can't do direct substitution because that point's undefined. So for some rules, let's look at a few rules. The limit of f of x plus g of x, say as x approaches a, tells us and this is true for subtraction too, we just take the limit separately, and these are all proven in the text. You're allowed to break them apart and take the limit of each one, as long as the limit of each one exists. So as I go down the line, I'm assuming that these limits exist. So this is as long as the limits exist. Multiplication. So I can break apart multiplication and division. Now division's a little different because the denominator can't be 0. So this says I can take the limit of the numerator and take the limit of the denominator separately as long as g does not equal 0 and the limit of g of x does not equal 0 as x approaches a. So you don't have 0 in your denominator. Okay, well let's look at an example. Let's look at the limit as x approaches 7, x squared minus x over 2x minus 1. Now on top I have a quadratic, and on the bottom I have a line. So I know the limits exist separately. As long as the denominator is not 0, I can take the limit of the numerator, limit of the denominator, and these, since the first is a parabola and the second is a line, I can do direct substitution. That means I just substitute 7 into the problem because the limit's going to be the same as the point. So this is going to be 49 minus 7 over 14 minus 7, and that's going to be 42 divided by 7, which is 6. Another one. Okay, now here h is approaching 0, and if you did direct substitution, you get 0 over 0. So that tells you that you have to keep going. You have to try something else. It's the point is undefined at h equals 0, but maybe not the limit. It's asking, what's it approaching? So it could be approaching a point that's not there, but that's still okay. So what we do in this example is we simplify it. We factor out an h in the numerator, and those cancel. And now we can use direct substitution, plugging in 0 for h, and we get 6x. Okay, so the point is if you get 0 over 0 for your limit, you have to keep going. That's just telling you that the point at 0 doesn't exist, but the graph could still be approaching something else. Okay, for a quick example, if you get something like this, you have to remember that a minus b can be reversed with just bringing out a negative sign. So see, if you substitute a 2 in here, you're going to get 0 over 0. Well, that tells you that there's no point at 2, but you can use the fact that you can reverse the order of the numerator and put a negative out front. Those are going to divide out, so that's just -1. So there is an answer to this problem, although the point doesn't exist. The limit exists, and that means it's still approaching that value. Also for here, you see separately that doesn't exist. But if you combine them first, you do a little work, and they have common denominators already. So my numerator is that which factors, let me put it in the right order, and now I can do direct substitution because that's a line. That means it's undefined at 1, but it's approaching 2. The y values approach 2, so that just means there's no point there, but it's still approaching 2. So something like this could happen. I'm not sure. You'd have to sketch. Well, yes, Sam. This is what it's going to look like exactly. That's at 1, and here's at 2. So as x approaches 1, your y values are approaching 2, so there is a limit, but there's no point. The point at 1 is undefined. Let's look at some more examples. Limit sine x, x approaches 0. Now, Triggs functions are nice and smooth too, so you can use direct substitution on those, and the sine of 0 is 0. Limit of cosine, same thing. Cosine is nice and smooth, and there's no breaks or nothing funny going on there, so you can just use direct substitution, and cosine of 0 is 1. Now, for the next one, you're going to have to do a little trick, because if you substitute in 4, again, you're going to get 0, 0, which tells you that the point is undefined at 4. So what we do here when you have a square root is you're going to rationalize the numerator here. And that's a little trick you're going to have to remember when you have a square root. If the square root's in the denominator, then you rationalize the denominator. So you multiply by the conjugate. In the numerator, you get x minus 4. In the denominator, you have x minus 4 times the square root of x plus 2. Those divide out. And now you can use direct substitution. So that's 1 over square root of 4 plus 2, and that's 1, 4. Whereas, again, if you substituted 4 into the numerator and denominator, you would get 0 over 0, which is not undefined in limits. As we see, you can go further, but you might have to use some tricks. Okay. And another topic that's important in this section is called the squeeze theorem. And that's really, really important. And it's just what it says it is. It says, basically, if you have a function in between two other functions, and their limits all exist, and say the limit at a point, and that's the same limit as g, then h gets squeezed in between the two of them, and you can say that the limit of h of x, which is in between, is also going to get squeezed out. And just briefly, what's going on here is that, okay, here's f, say, and here's g. Okay, let me do this. And say h is in between the two of them. And this point in this case is a. So as x approaches a, then f is approaching this value, and so is g approaching that value. So h also has to approach this value, and that value is L on the y-axis. Or another way it could happen is that here's f, and here's g, and h is in between. And as x goes to infinity, that's also true, then G is going to say L, this is L, and F is going to L, so H has to go to L. So it happened that way too. Okay, look at some of the example homework problems.